that this is the closure property table. You can find on internet also. I have also taken from the internet. You can just search for closure properties of languages, and you will find many closure property tables like this. So you can see here what is happening. Like if you see in this table, then this the first column is for regular languages. You can see these regular languages are closed under union. I told you. So this the proof and also everything we have already seen, that the regular languages are closed under union. They are closed under intersection, set difference, complementation, okay, concatenation, clean star, clean plus, reversal. Okay, all these operations we have already seen. Intersection. So you can see all these operations we have already seen that regular languages are closed. The proof of all these operations we have already seen. And there are many operations. You can define your own operation. Like there is no limit. There is no limit on the operations. But these the tick mark that I have, like all these operations that I have tick mark, these are important. And also there is one more important operation, that is homomorphism. These are the only important operations. Other these other things are not that important. You can skip these things. Anyway, these are not important. So today we will see what is homomorphism operation, and the set of regular languages, they are closed under homomorphism also. Okay, so you already know the meaning of closure property. These closure property are very important from the gate point of view. So when we say that set of regular languages are closed under concatenation operation, then what we mean? We mean that if you take two regular languages and then you do the concatenation of those, then you will again get a regular languages. Okay, then you will again get a regular language. This is the meaning. So you can see set of regular languages are closed under most of the operations. This we have already seen. I also told you about these things. And I also told you about four operations: subset operation, superset operation, infinite intersection, infinite union. Okay, all these four operations also I told you that regular languages are not closed under these operations. So these are those four operations: subset, superset, infinite union, infinite intersection. Those are the you can say most famous operations under which set of regular languages are not closed. Other all the standard operations that you can see: union, intersection, set difference, concatenation, clean star, reversal, complementation, all these standard operations that you can see, these set of regular languages are closed under those all operations. Now, so now today we will see the closure properties of CFL. So in this table you can notice few things. In this table you can see few things that if you see, these CFLs are closed under union. These CFLs are not closed under intersection. What is the meaning of not closed? The meaning of not closed means if you have two CFL and you take the intersection of those two CFL, then the result may not be CFL. The result may be CFL, the result may not be CFL. So we cannot guarantee that the intersection of two CFL will be CFL. So this is what we call not closed. Means we cannot guarantee that they will be, the intersection will be CFL. We cannot guarantee that. So you can see that's why this set of CFL, they are not closed under intersection. They are not closed under set difference. They are not closed under complementation. Okay. Now the set of CFL, they are closed under concatenation, clean star, clean plus. Okay, and you can see all other operations. If you see all other operations, then CFL are closed. So these are the three operations. These are the three important operations under which set of CFLs are not closed. Okay, so we will see why set of CFL are not closed under these operations. This also we will see. Now you can see this. Then we will see the closure property of DCFL. DCFLs are actually not closed under most of the operations. You can see no, 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 no. So you can see in regular languages we have yes, 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 everything yes, yes, means regular languages are closed under most of the operations. Set of CFL are also closed under most of the operations. These DCFLs are not closed under most of the operations. You can see no, no, most of the operations, they are not closed. Okay, CSL are closed under most of the operations. You can see recursive set of recursive languages, they are also closed under most of the operations, and set of RE languages, they are also closed under most of the operations. So now this is actually the closure property table. This is a very important topic from the gate point of view. So now today we will discuss the closure properties of CFL languages and also the closure properties of DCFL languages. Before that, let's see this operation, homomorphism. What is the meaning of this homomorphism operation? This is an important operation. Let's see. So what is homomorphism? Homomorphism is like this. Let's assume you have this alphabet. Your sigma is a comma b. This is your sigma. And let's assume over this alphabet you have a string. For example, a b a a. This is your string over this alphabet. Now homomorphism basically is a function. Homomorphism is a function from sigma to some for example, let's assume you have gamma. This is gamma. Let's assume this is gamma and this is 0 comma 1. This gamma is 0 comma 1. So this homomorphism is nothing but a function from sigma to gamma star. What is gamma star? Gamma star means strings, a set of strings over this gamma. So for example, here you will have epsilon, here you will have 0, here you will have 1, 0 0 0 1, and all these things. So now homomorphism is what? Homomorphism is a function, is a mapping from this set to this sigma star. For example, this a can be mapped to maybe 0 0. So this a is mapped to 0 0, because I told you this homomorphism is nothing but a function. This homomorphism is nothing but a mapping. Let's call it h. So let's assume that h of a is equal to 0 0, and let's assume h of b is equal to epsilon. Let's assume. So you can see now, if this is the situation, so basically you can say that the homomorphism of a is 0 0 and homomorphism of b is this epsilon. So now what will be the homomorphism of this a b a? So you see, you can very easily find out a is nothing but your 0 0, b is nothing but your epsilon. So dot epsilon, a is nothing but 0 0, a is nothing but 0 0. So finally what you will get? You will get 0 0 0 0 0 0. This is what you will get. So you can see this is how you this is the homomorphism operation. So what is homomorphism? Let me tell you. Homomorphism is a mapping from one alphabet. Okay, your alphabet like sigma 1, this is our first alphabet, and the second alphabet is some sigma 2. This sigma 2 can be same as sigma 1 also. So from this alphabet to sigma 2 whole star. So basically every symbol of this alphabet will be mapped to some string. Okay, some string of this sigma 2 whole star. Now this is called homomorphism. So this is our homomorphism. Now we will take some examples and we will see what it is. For example, let's assume sigma 1 and sigma 2, these are two alphabet. And remember, sigma 1, sigma 2, they can be same also, they can be different also. Basically, they are two alphabet. Okay, now homomorphism is what? Homomorphism is a function, okay, from sigma 1 to sigma 2 whole star. So basically every symbol, every input symbol of sigma 1 will be mapped to exactly one string of sigma 2 whole star. Okay, that associates each symbol in sigma 1 with string in sigma 2 whole star. Let's assume, for example, this is your sigma 1, 0 comma 1. As I told you, sigma 2 can be same also. Sigma 1, sigma 2, they can be same, they can be different. So you can see that now this is the mapping we have. This is the function we have from sigma 1 to sigma 2 whole star. So here what we are doing, the h of 0, this is epsilon, and the h of 1 is what? That is 1. So you can see this is also valid. Okay, you can see this is a mapping from sigma 1 to sigma 2 whole star. So this is your homomorphism. Now once you have this, like 0 is mapped to epsilon, 1 is mapped to 1, then how can you find the homomorphism of a string? Like this is the homomorphism of symbol, h of 0, h of 1. This is the homomorphism of input symbols. Now you can very easily find what will be the homomorphism of strings. For example, if you have this string 0 0 1 1 0, then what will be h of 0 0 1 1 0? This will be nothing but h of what is 0? H of 0 nothing but epsilon dot 1 dot 1 dot epsilon, and this is your 1 1. So you can see h of homomorphism of 0 0 1 1 0. What is this? This is nothing but 1 1. Okay, so this is your string, this is your homomorphism operation. Okay, anyway, so so basically this is called our homomorphism, and Now, let me take some example and let's try to understand this homomorphism operation. Assume that your sigma 1 is a comma b. This is your sigma 1. And assume that your sigma 2 is 0, 0. Let's assume. So your sigma 1 is a comma b and your sigma 2 is 0. And now we have a homomorphism. In this homomorphism, this h of a is 0 and this h of b is what? H of b is uh, you can say 0. So h of a is also 0, h of b is also 0. Now tell me what will be. So this is given, these things are given to you. Okay, these red color thing, these are given to you. Now you need to tell me what will be h of 0 power sorry, a power 4 b power 4, what it will be. Let's call it h star. Why I am calling it h star? Because h I am using for homomorphism. Basically this h, this symbol h I am using for homomorphism of input symbols, and this h star I am using for homomorphism of strings. Are you getting the point? Both are same actually, nothing difference, nothing different here. This h of a means homomorphism of input symbol a. This h of b means homomorphism of input symbol b. Okay, now what is this h star a power 4 b power 4? It means homomorphism of this string a power 4 b power 4. Okay, so what is h star a power 4 b power 4? Tell me. So basically, Harshita means 0 power 8. Okay. So you can see the homomorphism, the mapping of A is to 0 and the homomorphism of B is 0. So what is homomorphism of A power 4, B power 4? This is nothing but the mapping of A is to 0. So it will be 0 power 4, 0 power 4, which is finally nothing but 0 power 8. This is your homomorphism of this string. So this is how you can find, basically this is how you can find the homomorphism of a string. Let's take this example. Now once you have homomorphism of a string, then you can also define homomorphism of a language. So what is homomorphism of a language? Homomorphism of a language is nothing but is basically, let's assume you have a language L. Let's assume this is your language L. Then what will be homomorphism of L? This will be nothing but homomorphism of each string. Homomorphism of each string such that W belongs to L. Basically just do the homomorphism of each string in L, and that will be your you can say homomorphism of the language. Okay, so this is how you can find the homomorphism of a language very easily. Let's take the same example we are going to take. So your, let's assume your L, this you have this L and your language is a power n b power n such that n greater than equal to 0. This is your language, and let's assume that I have given you a homomorphism. H of a is 0 and h of b is 0. Now tell me what will be h of L? What will be the homomorphism of language L? Tell me what it will be. Try this. Are you trying, or shall I explain? Let me know. Okay, so see this example, and you can try the next example. You can try. So what is this? This is n equal to a power n b power n. This is your language, and the homomorphism is given to you. So the image of a is 0, the homomorphism of a is 0, and homomorphism of b is also 0. So this is the homomorphism given to you. Now he is asking what is the homomorphism of this language n. Homomorphism of a language is nothing but homomorphism of each string inside that language. And remember, homomorphism of a string is nothing but homomorphism of each symbol inside that string. So it's like this. What will be homomorphism of L? So each string you take and do the homomorphism of that string. For example, you take this a power 0, b power 0 you take. What it will be? A power 0, b power 0. This is your string in the language, you see. In this language, this string is there, a power 0, b power 0. Now what will be the homomorphism of this is nothing but basically this is your epsilon, so the homomorphism of this also will be epsilon. Okay, actually homomorphism of epsilon is always epsilon. Okay, the the h of epsilon is always epsilon. Anyway, so this is your homomorphism of epsilon. Another string that you have is a power 1 b power 1. Now what is the homomorphism of this string? Homomorphism of a string is nothing but homomorphism of each symbol inside that string. So in this string we have two symbols, a and b. So the homomorphism will be 0 power 1, 0 power 1, which is nothing but 0 power 2. Another string that we have is a power 2, b power 2. And now the homomorphism of a is 0, so 0 power 2. Homomorphism of b is 0, so 0 power 2. 0 power 2, 0 power 2 is nothing but 0 power 4. Similarly, you can check a power 3, b power 3, the homomorphism will be 0 power 6, and so on. So what will be your h of l? Means the homomorphism of a language. Homomorphism of a language is nothing but homomorphism of each string inside this language. So this will be nothing but 0 power m, such that m is even. So this is your h of l. Anyone has any doubt in this? Any doubt in this? Anyone? Aditi, Sanjeev, Harshita? In this homomorphism of language L, anyone has any doubt? Okay, so this is how you can find homomorphism of a language. So homomorphism is just a function from one alphabet to the set of strings of some another alphabet. So this this is the homomorphism operation, and this is important. For example, you can see, let's assume this is your sigma 1 0 1 2. This is your sigma 1, and this is your sigma 1 0 1 2. Consider this string 0 1 2 1. So you can see this is your string. Now let's assume your sigma 2 is a b c and so on. This is your sigma 2. Now we are defining a homomorphism. H of 0 is this, h of 1 is this, h of 2 is this. H of 0 means that's the way. H of 1 is, you can say, you who, and this h of 2 is I like it. So this is homomorphism, you can see. So basically the image of 0, image of 1, image of 2. Homomorphism of 0, homomorphism of 1, homomorphism of 2. Everything is given to you. Now if I want to find the homomorphism of 0 1 to 1, what it will be? It will be nothing but homomorphism of 0, homomorphism of 1, homomorphism of 2, homomorphism of 1. So what you will get? You will get homomorphism of 0, that is nothing but that's the way. Homomorphism of 1, that is this. Homomorphism of 2, that is this, and homomorphism of 1, that is this. So this is your homomorphism of 0 1 2 1. Okay, now so anyway, this is how the homomorphism operation is defined. Now we will see the homomorphism of a language. You can also check it out. So what is homomorphism of language? That as I told you, homomorphism of each string inside that language. This is how you can find homomorphism of a language. Okay, so try, for example, if you try this example, this is your language. Your language is this. This is the actually this is the regular expression for your language. 0 1 2 0 whole star. This is the regular expression for your language. So this is the language that is given to you. Now the homomorphism is also given to you. You can see that h of 0 is n, the h of 1 is y, h of 2 is a. So what will be the homomorphism of this language? As I told you, homomorphism of any language is nothing but homomorphism of each string inside that language. So your language is this 0 1 2 0 whole star. So actually your homomorphism will be, okay, just easily, okay, you can do replace this 0 with n, because the homomorphism of 0 is n, homomorphism of 1 is y, and the homomorphism of 2 is a. So this is what you will get. So this is the homomorphism of your language. Okay, so if your language is given to you in the regular expression format, then very easily you can find the homomorphism of that language. Just all you need to do is just replace each input symbol with its you can say with its image. Like this 0 can be replaced by n, 1 can be replaced by y, and 2 can be replaced by a. So this is your homomorphism operation, and this is how you can find the you can say homomorphism of a language. You can try this example also. So you have this language 0 1 1 star, this is the regular expression. So the regular expression is given to you, and from regular expression you can very easily find the homomorphism of this language. All you need to do is just replace each symbol in the regular expression by its image. For example, the homomorphism is given to you. He's saying that h of 0 is here and h of 1 is kitty. So this homomorphism is given to you. Now you can very easily find the homomorphism of this language. So the homomorphism of 0 is here, and homomorphism of 1 is kitty, and the homomorphism of 1 is kitty. So finally you will get here kitty kitty star. So this is how you can find the homomorphism of a language. If the language is given in the regular expression format, then you can very easily find it out. All you need to do is just replace each input symbol with its homomorphism image. Okay, if the language is given to you as a set of strings, like I gave you a power n b power n, that language I gave you, in this situation you can find the homomorphism of a language very easily by finding the homomorphism of each string in that language. Okay, so this is your homomorphism, and this operation is important operation from gate point of view also. You can check it out in the previous year gate exam. I think 3 or 4 or 5 times they have asked questions from homomorphism, so you can just check it out. Anyway, now we have this result. Actually, we won't prove this result. We have already proven many results on the closure properties of regular languages. Like I have already proven that if you have two regular languages and you take the union of these two regular languages, then you will get another regular languages. So that was your closure property of regular languages under union operation. So similarly, intersection, complementation, concatenation, all these things we have already proven. But a set of regular languages, they are closed under homomorphism also. So if you have a regular language, okay, and also you have a homomorphism. Now if you find the homomorphism of that regular language, so remember, homomorphism of a regular language is also regular language. So we can say that set of regular languages are closed under homomorphism operation. Okay, so the proof of this thing, like there is no requirement to see the proof. The proof is quite long, so there is no need of proof right now from the gate exam point of view. Okay, just this result is enough that set of regular languages are closed under homomorphism. Basically, if you have a regular language L, so L is regular language, okay, and some homomorphism is given to you, then h of L will also be regular. Okay, so regular languages are closed under homomorphism operation. So this is an important result. Now all the important closure properties of regular languages are already over. You can see the set of regular languages, or you can say the regular languages, they are closed under union, intersection, complement, concatenation, clean closure, and string homomorphism. All these things we have already seen. Like in the set difference also we have seen that regular languages are closed under set difference and all those things. Clean plus, set difference, reversal, all these are very standard operations, and the set of regular languages are closed under all these standard operations. Of course, when you go to the internet and you check it out, like closure properties of regular languages, or closure property of any language, then of course you will find big tables you will find. Okay, there will be big tables. In those tables you will see there are 10, 15, 20 operations are there, but there is no requirement to buy hard that table. Do not buy hard that table. There is no need. At least for the regular languages you don't have to buy hard that table, because we have already proven all these things. We have proven, like string homomorphism we did not prove because it will take like more time to prove. That's why I have not proven the closure of regular languages, closure property of regular languages under homomorphism operation. But under all other operations, all other these standard operations, I have already given you the proof. You must know the proof. Okay, so anyway, now we will see the closure properties of CFL languages. So closure properties of context free languages. The context free languages, they are actually closed under. So now actually before we, so anyway, this is just again, you can see if L1 and L2 are regular, then you know that complement of regular is regular, union of two regular is regular, intersection of two regular is regular, concatenation of two regular is regular, clean star of a regular is regular, and the homomorphism of regular is regular. All these things we have seen. Now we will see what are the properties, which of these properties you can say CFLs are closed. So let's see. So the first operation that we will see today is union. Let's see that CFLs, actually CFLs are closed under union operation. CFL, the set of CFL, they are closed under union operation. You can prove it very easily. You can prove it by PDA. Let's assume L1 is CFL and L2 is CFL. If you have two CFL, then because this L1 is CFL, so you have a PDA. So let's call it PDA P1. Because this L2 is also CFL, so you have a PDA for L2 also. Now you can make PDF for P1 union. You can make PDF for L1 union L2 very easily. You can make a PDF. How to make PDF? As I told you in the last lecture also, this is how you can make a PDF. Okay, so this is how you can make PDF for L1 union L2. Now this is your PDA for L1 union L2, because all the strings of L1 you can accept here and all the strings of L2 you can accept here. So this is how you can make a PDA of L1 union L2. So it tells you that L1 union L2 is also CFL because we have a PDA. Because we have a PDA, so L1 union L2 is CFL. As I told you, CFL are basically CFL correspond to PDA. Every PDA generates accepts a CFL language, and every CFL language is accepted by some PDA. All these things we have already seen. Anyway, so you can see set of CFL languages, they are closed under union operation. Let me repeat it once again, that what is the meaning of closure property. Let me repeat. When you say that something is closed, when you say that something is closed, let's assume I am saying that union of CFLs, the set of CFLs, they are closed under union operation. What I mean this: you can take any CFL, and if you take the union of two CFL, then the result will, this union of two CFL, this also will be CFL. So that's why we say that they are closed. Closed means basically you can take any CFL, the union will guaranteed to be CFL. Like this will guarantee to be CFL. Okay, it is guaranteed that it will be CFL. So this is what we call closed, means set of CFL languages are closed under union operation. Okay, and this closure property we have already seen in the group theory also. Basically the results should not go out. Your base set is set of all CFL languages. This is your base set of all CFL languages. Okay, now if you take two languages from here and you apply the union operation, then the result will also belong to the same base set, means the result should also be CFL. This is the meaning of closure property, and this is the meaning of closed. What is the meaning of not closed? What is the meaning of not closed? The meaning of not closed basically means that you cannot guarantee. What I want to say, I want to say that when you say that something is not closed, then it means, for example, now we will see, actually just in 5 minutes we will see that set of CFLs are not closed under intersection. What it means? It means that if I give you some CFL L1, let's assume I give you some CFL L1, and I give you another CFL L2. Now this intersection, if you take, okay, see intersection of this CFL, intersection of basically intersection of two CFL, if you take, then this result may not be CFL, may not be CFL. So this result may be CFL, may not be CFL, and that's why we say that set of CFL are not closed under intersection operation. Because if you take intersection of two CFL, if you take intersection of two CFL, then the result may not be CFL. Okay, we will see example. We will see such an example where the intersection of two CFL will not be CFL. This example we will see. Anyway, this is the meaning of not closed. Let's see the so the union of two CFL, the proof we have already seen. We have seen the proof using the PDA, but you can also see the proof using grammars also. Because if your L1 is CFL, let's assume your L1 is CFL, L2 is CFL, then because L1 is CFL, so you have a CFG. Let's call it G1. Because this L2 is CFL, so you have some CFG, call it G2. So for every CFL, you have some CFG which will generate that CFL. Similarly, every CFG generates a CFL. So anyway, because this L1 L2 both are CFL, so we have CFG G1 and G2 like this. Okay. Now if you take the, like if you make like this, let's assume you make like this. So this is your complete, like, okay, let's assume this is the start symbol S1, and this is the CFG of G1, and this is the CFG of G2. So in G2 the start symbol is S2, and in G1 the start symbol is S1. So this is your CFG for G1. Sorry, this is your CFG G1 and this is your CFG G2. Then how can you make CFG for L1 union L2? Very easy. Just add a new start symbol and send it to either S1 or S2. Either S1 or S2. So just, okay, now you can see this complete thing will generate L1 union L2. How it will generate L1 union L2? You can see very easily. You can see, because this S can either go to here or it can go to here. If this S will go to S1, if this S will go to S1, then this S1 will generate what? This S1 will generate L1, because this G1 is the grammar for L1. Now this S can go to S2 also. When this S will go to S2, then you know that this S2 is a starting symbol of G2, and G2 is the grammar for L2. So you can see that when this when this S goes to S2, then you will generate L2. So you can generate L1, you can generate L2. Basically, you can say this grammar will generate L1 union L2. And you can see this grammar, is a context free grammar, because in the context free grammar in the CFG, what is the restriction? The restriction is that on the left side of the production, on the left side of every production, you must have exactly one variable. You can see this condition is satisfied, because on the left side of this all the production, on the left side of every production, you have exactly one variable. So that's why this is a CFG, and this CFG is generating what language? That is L1 union L2. So this is the proof that set of CFLs, okay, you can say that set of CFL are closed under union operation. This is how you can very easily make give the proof. So we have seen the proof using PDA, we have seen the proof using CFG. But the important result that you have is that set of CFL are closed under union operation. If you have two CFL, then their union will definitely be a CFL. Okay. Now let's see set of CFL. They are not closed under intersection. They actually set of CFL. They are not closed under intersection. Not closed. Intersection, not closed. What is the meaning of not closed? So the meaning is like this. If you have two CFL, then their intersection may not be CFL. Their intersection may not be CFL. Consider this CFL. Okay, let me give you a CFL. A power n, B power n, C power m. First of okay, before we see some example, first let's try to see whether this is a regular language, CFL language, DCFL language, what it is. So try to see what it is. Tell me what this language is. Is this regular? Is this DCFL? Is this CFL? Anyone want to try? In the last lecture, we have already seen how to detect whether a given language is regular. So at least you should know how to check for regularity. Anyone want to try, or should I explain? Aditi, Harshita, Sanjeev. Okay, let's see. This is not regular. This is not regular because you can see here we need to do the matching here. Here we need to do the counting because you see number of A should be equal to number of B. So we need to do the counting. We need to count how many A are there. Okay, then we need to match them with number of B's because A power n B power n means number of A should be equal to number of B's, you can see. So we need to do the counting, and you can see this n can take any value. This n actually can take any value greater than equal to 1. So this n is unbounded. Okay, there is no bound on n. This n can take any value, 1, 10, 100, 1000, 1 billion, 1 trillion. This n is unbounded. This can take any value. So basically we need to do the unlimited counting. Like there is no limit. There is no limit on the counting. We need to count number of A's, and your, as I told you, your DFA cannot do the unlimited counting. That's why this A power n, B power n, this thing cannot be handled by your DFA. So this is not a regular language. This is not regular, okay, but this is DCFA. Okay, let me tell you why this is a DCFA. See, a language is DCFA if you can, very certainly, if you can say when to push, when to pop. Like there should be certainty in the push and pop. This is the meaning basically. Okay, if you have very, you can say very certain choice. Okay, you can certainly say, okay, that this to push, this to pop, when to push, when to pop, everything. If you can certainly say, then that is a DCFR language. Here you can see this is DCFR. Why? Because what you will do, you will push all the A's. So this pushing is very clear because in the beginning A will be there, and you will push all the A's. You will just keep on pushing all the A's, A. You will just keep on pushing. Okay, so you will push all the A's. Now after this, what you will do, once you see a B, okay, as soon as you see a B, what you will do, you will start popping. So you can see one thing is clear, that the push and pop are very clear, because in the beginning when you see A, then you need to push, and then any number of A you can see, and you will push. As soon as you will see a B, as soon as the first B will come, what you will do, you will start popping. So you can see the push and pop are very clear, and there is certainty here, like when to push, when to pop. In the beginning you need to push because you are you can see number of A's, so you need to push, and as soon as you will see a B, you will start popping. Okay, so basically everything is clear, and this basically this C power m is greater than equal to 1. This m has nothing to do with n, so this thing is actually doesn't matter to us, because this is just like C plus. This C power m is just like C plus, clean plus, C plus. So you can see this actually does not matter. You can just skip any number of C's. You will just skip any number of C's. So this is your DCFL. Okay, this is how you can check whether a given language is DCFL or not. Now let's check this language, A power m, b power n, c power n, m comma n greater than equal to 1. Tell me, is this language regular, DCFL? What it is? Tell me. Is it regular? Is it DCFL? Try this. Any doubt in these things? These things we have already seen in the last class also. Okay. If anyone has any doubt, then you should ask so that I know where you are getting doubt so that I can clear. Okay, so let's see. This is also not regular because what it is saying any number of a, okay, a power m. You can see this m has nothing to do with n. You can see this m has nothing to do with n. Anyway, so this a power m basically says that any number of a can come. Okay, any number of a can come. After this thing should equal means b power n, c power n. What it means? It means number of b is equal to number of c. Now this thing actually cannot be done with the DFA because again this is just a unlimited counting. Okay, b, you need to count number of b's because number of b's should be equal to number of c. This is the condition, and that's why you need to count the number of b's. But this unlimited counting, this n is unbounded, you can see. So this unlimited counting cannot be done by DFA. Okay, so that's why this is not regular. This is DCFL. This is clearly DCFL. Why this is DCFL? Because push and pop is clear. Why? What you will do initially, if you see any number of a, you will just skip. Okay, just skip. Keep on skipping. As soon as you will see the first b, you will start pushing. So you will push. Then as soon as you will see the first c, okay, as soon as you see the first c, you will start popping. Okay, so you can see the push pop is everything is clear. What to push, what to pop, how much to push, how much to pop. Okay, and when to push, when to pop, everything is clear. Everything is clear. Okay, when to push, when to start pushing, when you see the first b, at that time you need to start the pushing. Okay, so when you encounter this b, then you will start pushing. Okay, and then you will just keep on pushing all the b's. Now when to start popping, when should we start popping? You will start popping when you encounter c. So when you encounter this c, okay, when you encounter this c, then you will start popping. Okay, so when to start pushing, when to start popping, everything is clear. Now how much to push, how much to pop, everything is clear. For example, here you can see for every b you will push one b, and for every c you will pop one b. So everything is clear. That's why this is a DCFL. Okay, so this is a DCFL. Now every DCFL is a CFL. So you can see these two languages that we have seen. This is the first language we saw, a power n, b power n, c power m. Okay, where n m greater than equal to 1. So this was the first language. And the second language was a power m, b power n, c power n. Okay, n comma m greater than equal to 1. So this also we have seen, this is DCFL. This also we have seen that this is also DCFL. Every DCFL is CFL. So both of these languages are CFL. You can see both of these languages are CFL. Now, what is the intersection of these two languages? Anyone want to try this? What is the intersection of these two languages? Tell me. What is the intersection of these two languages? Try this. Find the intersection of these two languages. What is the intersection? You just need to find the intersection. Like the first language is a power n, b power n, c power n. The second language is a power m, b power n, c power n. Now, what will be the strings in the intersection? I am just asking what will be the strings in the intersection. Means what is the intersection language? See, the intersection of these languages will be a power n, b power n, c power n. This is the intersection. What is the intersection of two languages? This is the first language, okay, and this is the second language. Two language is nothing but a set. So I am asking the intersection of two set. What is the intersection of two set? That is nothing but the common things. Means those strings which are here also and here also. What are the strings here? Here we have this type of string, a power m, b power n, c power n. This type of string we have here. And this type of string, a power n, b power n, c power m, this type of string we have here. Then what will be the common string? You can see here we have a power n, b power n, c power m. Means here the strings are like this: a power n, b power n, c power m. In the first language, these are the strings. So this number of a should be equal to number of b. And in the second language, we have number of b should be equal to number of c. So in the intersection, this also should be satisfied, this also should be satisfied, because intersection means those strings which are here also and which are here also. Means basically those strings in which this should be equal and this should be equal. Means basically this also will be n. So this is your intersection. Your intersection will be a power n, b power n, c power n. These strings will be in your intersection n greater than equal to 1. Any doubt in this, anyone? This will be your intersection. Intersection of two languages you need to find. Every language itself is a set. I told you language is nothing but set of strings. So basically you need to find the intersection of two set, and the intersection of two set is nothing but the common elements, and you can very easily find the common element here. In the first language you have those strings which have a power n, b power n, c power n. In the second language, you have those strings which have a power m, b power n, c power n. So the intersection will be a power n, b power n, c power n. You can check it out. This a power n, b power n, c power n, we have already seen in the last lecture that this is not CFL. This we have already seen. I told you about this language that this is not CFL, because you need to compare this and you need to compare this. You can see, because we need to compare a number of a with number of b, then we need to compare number of b with number of c. But as soon as you compare number of a with number of b, as soon as you do this comparison, okay, now you don't have anything left to compare with number of c. So this we have already seen in the last lecture also, that this language is not CFL. This we have already seen. So what it tells you? It tells you that you have two CFL and their intersection is not CFL. You can see here you have two CFL and their intersection is not CFL. So basically you can say that CFL are not closed under the set of CFL. They are not closed under intersection operation. Is this point clear? Any doubt in this? Because you can see this language is CFL. Let me tell you. Let me see. You can see this language is CFL. This language is CFL, but the intersection is not CFL. Okay, intersection is not CFL. So it tells you that the CFL, the set of CFL, are not closed under intersection. Okay. Also, in this example, you can also see one thing. Actually, this is DCFL, this is DCFL, but the intersection is not DCFL. So in this same example, you can also say that DCFL are also not closed under intersection. So this example is enough to prove this example is enough to prove that set of CFL are not closed under intersection, and set of DCFL are also not closed under intersection. Okay. Anyone has any doubt in this? Okay, so now we will see the concatenation of CFL. The concatenation of two CFL is actually CFL. Very easily you can do this. Very easily you can prove this also. Let's prove it. Let's assume this is L1 is CFL, because this L1 is CFL. L1 is CFL. Let's assume L1 is CFL. So you have CFG G1. So this is the CFG G1. Let's assume this is the starting symbol of this G1 CFG. Okay, this L2 is also CFL. So because this L2 is CFL, so you have CFG G2. So you have CFG G2 for L2. Let's assume this is the starting symbol of this G1, and this is the starting symbol of G2. Okay, so now you want to find the context free grammar. You want to find the CFG for L1.L2. L1.L2. Very easily you can find. What you need to do, just make a new start symbol. You make a new start symbol and you send it to S1.S2, means S1 S2. Okay, now you can see this complete thing will accept L1.L2. Why? Because this S will go to S1 S2. This S1 will generate L1, this S2 will generate L2. So basically you will get L1 L2, L1.L2. This is how you can find concatenation. You can see this is a context free grammar, because on the left side of every production you have exactly one variable. So this is a CFG. So we have CFG for L1.L2. So what it tells you, it tells you that the set of context free languages, they are closed under concatenation operation. Okay, so the set of CFL are closed under concatenation operation. Now wait a second. Okay, so now let's see clean star. So if you have a CFL, let's assume L is CFL, then the L star will also be CFL, means the set of CFL are closed under clean star operation. And this also you can very easily prove. Let's assume this is the CFG for language L. So this is the CFG for language L. Then you can find CFG for L star like this. X will go to EX slash epsilon. So this is how you can do. Okay, let me solve it. Let's see here. So let's assume your language is CFL. Because your language is CFL, so you have CFG. So you have CFGG. So let's assume this is your CFGG, and the starting symbol is S1. So this is your CFGG. The language of this CFGG is nothing but L. Now you want to find the CFG for L star. Very easily you can find. Just make a new start symbol. Okay, and you can send this to like this S1 as epsilon. What it will do, actually, this complete thing is your CFG. This complete thing is your CFG for L star. Once you add this production, you will see that this complete thing is your CFG for L star. Basically you add a new start symbol. So this S is your new start symbol, and like this S1 as epsilon. Why this is L star? Because you can see, first of all, this can generate epsilon. Okay, because L star is what? L star is nothing but L power 0 union L power 1 union L power 2 union L power 3 and so on. So L power 0 is nothing but epsilon that is generated. You can see L power 1. How to generate L power 1? L power 1 means L. So you can generate very easily. What you do, this S can go to epsilon. So finally, basically, you will only get S1, or S1 will generate L. So this L can be generated. How to generate L dot L? Very easily you can generate. How to generate? S will go to S1S. Now this S will go to S. Now this S will go to S1S. Now this S can go to epsilon, so you will get S1 dot S1. S1 dot S1 will generate L square. Similarly, you can generate L cube and so on. So you can see this complete thing is context free grammar CFG for L star. So this is how you can find. So this proves, okay, so this is a proof that the set of context free languages are closed under clean star operation. Okay, similarly you can find that the set of context free languages, they are closed under clean plus operation also. Okay, anyway, so so this is the proof. Now let's see the some other operations. So we have seen union, we have seen concatenation, we have seen intersection, we have seen clean star. Now we will see something called complementation. So the set of CF are not closed under complement operation. They are not closed. So let's take one example and let's try to find out. So let's take this example, the language the same language I am taking, a power n b power m, so sorry, a power n b power n c power n, this same language I am taking. N is equal to a power n b power n c power n, such that n greater than equal to 1. So this same language I am taking now. So this is your language. You can see that this language is not CFL. This we have already seen in the last lecture. What will be L complement? What will be L complement? L complement means sigma star minus L. So or L complement means basically those strings which are not in L. Those strings. So what are the strings which are not in L? Okay. So those strings which are not in L. So you can see. We will have this type of string where like your L complement will be like union. It will be like this, either a power n b power n, but c power m means basically, oh, wait a second, let me take. So this is your example, a power n b power n c power n greater than equal to 1. So we know that this is not this is not CFL, this you already know. But in the L complement, in the L complement you will have those strings which do not have this a star b star c star form, first of all. Okay, so basically in your L complement you will have those strings which do not have a star b star c star form. Okay, so basically because here you can see the all the strings are of this form, a power n b power n c power n. So in your L complement you will have, first of all, you will have those strings which do not have a star b star c star form. So I can say like this, from sigma star you can minus the those strings which have this form, a plus b plus c plus, this type of strings you can subtract. Okay, so all those strings which do not have this type of form, those strings will definitely be in complement. Okay, union. Now those strings which have this form, in those, what type of strings will be there? You can see this type of string, a power m b power uh, n and c power p, such that you can say either m is not equal to n, or n is not equal to p, or m is not equal to p. You can see. So this is your L complement. Did you get this L complement? Anyone has any doubt in this L complement, then let me know so that I explain it again if you did not get this L complement. Anyone? this is your language L, and I am finding L complement. So this is L complement. Anyone has any doubt in this? In this L complement? Yes. So basically in this L complement, what is this? This is just those strings which do not have a plus b plus c plus form, you can see. Okay, because those strings will definitely be in L complement. Okay, so that's why I am including those strings which do not have a plus b plus c plus form. So those strings I am including in the L complement. Now those strings which have a plus b plus c plus form, from those strings, what type of strings I should include? I should include those strings where either m is not equal to n, or n is not equal to p, or m is not equal to p. These type of strings also I should include. Now this is your L complement. What you can notice from L complement? L complement, first of all, see this a plus b plus c plus, this is nothing but regular. A plus b plus c plus, this is regular. Sigma star is also regular, and we know that regular languages are closed under set difference. So this complete first box is regular. So this complete first box is regular actually. This is regular. Now let's see this part. A power m, a power m, b power n, c power p, where either this or this or this. So you can see m not equal to n. This is your CFL. Like finding out, like this is your CFL. Okay, basically we want this language where m is not equal to n, this language. So just one comparison, we need to compare the number of a with number of b, such that number of a should not be equal to number of b. So this is CFL. Similarly this is also CFL. Similarly this is also CFL. So CFL union CFL is already CFL, we have already seen. So this CFL union CFL union CFL, everything. So basically you can see this is your CFL. Okay, so this is CFL and this box is regular. CFL union regular. See, every regular language is CFL. You already know this thing. Every regular language is DCFL. Every DCFL language is CFL. So every regular language is CFL. So this language is also CFL. This language is also CFL. So the union of two CFL is also CFL. So this L complement is CFL. This L complement, this is CFL. So this language is CFL. This language is CFL, but this language is CFL, but its complement is not CFL. Its complement is not CFL. What it tells you? It tells you that the set of CFL are not closed under complementation operation. Anyone has any doubt in this? Let me know quickly. Anyone has any doubt in this? So you can see the complement of CFL is not a CFL. So what it tells you? It tells you that the set of CFL are not closed under complementation. And this is the counterexample. This is the proof. This is the counterexample, and we have proven that set of CFL are not closed under complementation operation. Set of CFL are already not closed under intersection operation. This also you know. Okay. So anyway, so these are the also because set of CFL are not closed under intersection, set of CFL are not closed under this complementation. So set of CFL are also not closed under set difference. Okay, so the actually the basically if you have CFL minus CFL, let's assume this L1 is CFL and L2 is CFL, then the set difference may not be CFL. Okay, very easily you can prove it. There is nothing, it's not hard. Okay, how to prove it? Very easily you can see. Let me show you how to prove it. See, let's assume this is your set A, this is your set B. So this is your set A, this is your set B. Now what is A intersection B? A intersection B is nothing but A minus B. Okay, this is your A minus B. Okay, so wait a second. What is your A intersection B? Let me tell you. A intersection B is nothing but A minus B. Because see, what is A minus B? This is A minus B. This is A minus B. Now, what is A minus B? That is this area. So you can see A intersection B is nothing but A minus B. Now we have already proven that the set of CFL are not closed under intersection operation. So we can also say that set of CFL languages are not closed under set difference. Why? Because if you assume that set of CFL languages are closed under set difference. If you assume that, then what will happen? Then this will be CFL, because you are assuming that set of CFL are closed under this set of CFL are closed under a set difference operation. This you are assuming. So A minus A minus B will be CFL. Okay, and this A minus this CFL minus CFL, this also will be CFL. So what it tells you? It tells you that intersection will also be CFL. So this is the problem. We have already proven that set of CFL are not closed under intersection. Okay, so if we assume that set of CFL are closed under set difference, then it will contradict our previous proof. Our previous proof was saying that set of CFL are not closed under intersection, but you can see there will be a contradiction. Hence, we can say that set of CFL are not closed under set difference operation. So this is how you can very easily prove. So these are the closure properties of CFLs. Okay, so CFLs are closed under all these operations, and only the three operations under which CFLs are not closed, those operations are, you can see these operations, you can see here in the first slide. You can see the first slide that we have is this. You can check out. So you can take it out here. So the CFL are closed under most of the operation. We have already proven that CFL are closed under union. CFL are not closed under intersection, not closed under set difference, not closed under complementation. So you can see CFL are not closed under these three operations. We have already proven that CFL are not closed under intersection, CFL are not closed under set difference, CFL are not closed under complementation. And all the remaining operations CFL are already closed. You can see the CFL are closed under homomorphism, the CFL are closed under reversal, clean plus, clean star, concatenation, intersection with regular languages. Remember one thing, okay, remember this is an important thing. CFL, intersection CFL, this may not be CFL, this may not be CFL, this may not be CFL. Okay, CFL intersection CFL, this may not be CFL, but regular intersection CFL will definitely be CFL. So I can say that set of CFL are closed under intersection with the regular language. So this I will write intersection with regular language. So what I can say that if you have a CFL and you intersect it with some regular language, then the result will also be a CFL. Remember, CFL intersection CFL may not be CFL, but CFL intersection regular will definitely be a CFL. So this is the meaning of this is the meaning of this intersection with regular language. Means if you have a CFL, you do the intersection with regular language, then the result will definitely be CFL. So this is the closure property table of CFL. This is the closure property table of regular languages. Now, similarly, you can actually, we have seen the proof of many of the closure properties of regular languages. We have seen the proof of many of the closure properties of CFL languages also, but we will not see the proof of the proof of closure properties of DCFL languages. We won't see those proof because those proof are beyond the gate level. So right now we don't need them. But I will just give you some counter example. Like I will show you how DCFL are not closed under union. Let me show. So you have two DCFL. Consider these DCFL: A power n, B power n. This is DCFL. You already know. So this is DCFL because push and pop is very clear, and we have already constructed DPDA for this language. If you remember, when I was teaching DPDA, PDA, at that time we have already constructed DPDA for A power n, B power n. So this is DCFL. And another DCFL that I can take is A power n, B power 2n. So this is also DCFL. This is also DCFL. Two DCFL we have. But if we do the union, A power n, B power n, union A power n, B power 2n, now this is not DCFL. This is not DCFL. And we have already seen in the last lecture why this is not DCFL. The reason this is not DCFL, what is the reason? Reason is this: because the push and pop is not clear. Like in the beginning, you are in the starting state. In this starting state, you don't know whether the string belongs to this part or whether that string belongs to this part. You don't know. Because if the string belongs to this part, then for every A, you will push one A. Okay. But if the string belongs to this part, then for every a you will push two a's. So you can see the push and pop is not clear, because in the beginning, in the initial state, you don't know to which of these languages, to which of these languages your string belongs. So that's why the push and pop is not clear. That's why this is not DCFL. This union is not DCFL. Remember, this is DCFL, this is DCFL, but the union is not DCFL. What it tells you? It tells you that set of DCFL are not closed under union operation. Okay, so this is the proof that set of DCFL are not closed under union operation. Now, set of DCFL are not closed under intersection also. This we have already seen. Like when I gave you the proof of the set of CFL are not closed under intersection. In that proof, I also proved that because we took two DCFL, if you remember, we took two DCFL. These were the two DCFL we took: A power n, B power n, C power n. This was one DCFL. Another DCFL was this: A power m, B power n, C power n. This is another DCFL. So we have two DCFL, but their intersection was A power n, B power n, C power n. You can see the intersection was not DCFL. This is not DCFL. So DCFL intersection DCFL was not DCFL. So what you can say? You can say that DCFL are not closed under intersection operation. Okay. So we have seen these two things. Now DCFL are not closed under reversal also. Why? Take this. Take this example. Take this example. C A power n, B power n union D A power n, B power 2n. First of all, tell me whether this language is DCFL or not. Try this. Just try this. Just think about it. Is this language DCFL? Tell me. Aditi, Harshita, let me know. Is this language DCFL? So this is DCFL. Yes, this is DCFL. Why this is DCFL? Because now push and pop everything is very clear, very clear. Why? Because in the beginning, okay, if I give you some string, then you can very clearly say whether to what to push, what to pop. Everything is clear. Why? Because if the first symbol is C, if the first symbol is C, if the first symbol is C, then what you will do? Okay, if the first symbol is C, then what you will do? Then you will do the A power n, B power n. Okay, so then you will do this. Basically, if the first symbol is C, then you will push one A for each A. Okay, if the first symbol is D, then you will do A power n, B power 2n. So you can see now the push and pop, everything is very clear. So this is DCFL. But now what is the reverse of this? Okay, what will be the reverse of this language? Let's see. So this language L is definitely this is our language L. This language L is definitely DCFL. But what is reverse of L? The reverse of L will be What is this? The reverse. You do the reverse, then what it will be? It will be basically like this: b power n a power n c union b power 2n a power n d. Is this language regular? Tell me. Sorry, is this language DCFL? Is this language DCFL? Tell me, is this language DCFL? So you can know, actually this is not DCFL. Why this is not DCFL? See, now you don't have any way to determine what to push, how much to push. You don't know. Because see, here actually this first symbol C, this first symbol D, they were telling you what to do. This C was telling you that okay, push 1A for each A. This D was telling you that push 2A for each A. So this A, C and D were telling you everything. Now nothing can tell you anything, because now you see in the beginning there is nothing that can tell you what to do. For example, you do not know, okay, when you see the first B at that time, when you see the, you are in the initial state, in this initial state when you see the first B, at that time you do not know whether to do this or whether to do this. So this is not clear. Okay, whether to do this or whether to do this, so this is not clear. So you can see that now this push and pop is not clear. What to push, how much to push, these things are not clear, because when you see the first B, at that time you don't know whether your string belongs to this part or whether that string belongs to this part. So that's why this LR is not DCFR. Is it clear, Aditi? Any doubt? Any doubt in this? Okay, so you can see this LR is not DCFL. This L is DCFL, LR is not DCFL. What it tells you? It tells you that the set of DCFL are not closed under reversal operation. The set of DCFL. The set of DCFL are not closed under reversal operation. You can see, because this is a DCFL and the reverse of this DCFL is not a DCFL. So this is your property. Anyway, so you can see most of the operations, these set of DCFLs are not closed under most of the operations. We have seen set of DCFL are not closed under union, intersection. They are not closed under set difference also. Okay, very easily you can prove it that because I already told you that A intersection B is nothing but A minus B. This we already know. So we have already seen that set of DCFL are not closed under intersection. This we have already seen. So it tells you that set of DCFL are also not closed under set difference. So you can see set of DCFL are not closed under union, set of DCFL are not closed under intersection, set difference. Okay, and other operations like concatenation, reversal, homomorphism. Actually, you can see most of the operations actually these DCFL are not closed. The two operations under which they are closed, these are like this. Okay, so the most important thing is that DCFLs are closed under complementation operation. What it means, the complement of DCFL will also be a DCFL. This is the meaning. If you have a DCFL, the complement of a DCFL is also DCFL. This is important property. We won't see the proof of this because the proof of this property, the proof of this closure property is beyond gate level, so there is no need to see that right now. But this result is very important. Okay, complementation of DCFL is DCFL. If you have a DCFL, you do the complementation of it, then the resulting language will also be a DCFL. So this is important, and with this our closure properties are over. Also remember this DCFL intersection DCFL is may not be DCFL. This we have already seen, because DCFL are not closed under intersection. So DCFL intersection DCFL may not be DCFL, may not DCFL, may not be DCFL, but regular intersection DCFL will definitely be DCFL. Okay, if you have a regular language, you have a DCFL language, then the intersection of regular language and DCFL language, that will definitely be a DCFL language. Okay, so this is like we can say that set of DCFL languages are closed under intersection with the regular languages. Okay, set of DCFL languages are closed under intersection with regular languages. So this is your closure property table. So we have seen the these regular languages, CFL languages, DCFL languages. We have seen the closure properties of these three languages. Okay, now after this is over, actually we will study these languages. For example, we will study something called Turing machine. At that time, we will study RE languages. So actually, as I told you in the first lecture, in the second lecture of TOC, I think in the first or second lecture of the TOC, I told you that every regular language is CFL. Sorry, every regular language is DCFL. Every DCFL is CFL. Every CFL is CSL. Every CSL is recursive. Every recursive is RE. Okay, so we will study these things from tomorrow onwards. From the next lecture onwards, we will study these RE languages. We will study REC languages. We will study Turing machine. But let me just tell you the closure properties here, and I will prove it, and I will prove these closure properties at a later point of time. Okay, when we will study Turing machine, at that time I will prove. At that time, I will prove these closure properties. But right now, just for the, you can say, just for the sake of completeness, let me cover it. The set of CSL are closed under most of the operation, you can see, because they are closed under, oh, you can see most of the operation. Okay, under all the standard operations they are closed. So you just need to know these standard operations, as I told you, till this homomorphism, all are standard operations. Last four operations you don't need to see. Just okay, last four operations you can cancel it out. Okay, just you need to remember these till homomorphism, these are the standard operations. So you can see the set of CSL are closed under all the standard operations except homomorphism. This set of CSL, they are closed under all the operations, you can see. So very easily you can just remember it, because there is nothing to remember. You can just remember that set of CSL are closed under most of the operations, you can see, except homomorphism. All the standard operations, they are closed. Similarly, set of recursive languages also, they are closed under all the standard operations except homomorphism. You can just check it out. So set of recursive languages, they are also closed under all the standard operations except homomorphism. Now coming to RE languages. RE languages are closed under all the operations. The set of RE languages are closed under all the operations except complementation and set difference. Except this operation, complementation and set difference. These are the only two standard operations under which set of RE languages are not closed. So this is your closure property table, and this is the discussion on the closure properties of languages. So this much discussion is enough, and we have already seen the proof of these things, and some of the proof here we have seen, and some of the proofs we will see at a later point of time once we study Turing machine, once we study RE languages, REC languages. At that time we will see the proof. But right now, this is your closure property table, and this closure property chapter is important chapter from GATE point of view. Many times they ask questions from this chapter. Okay, so let me see what is remaining. Let me see. Homomorphism we have already seen. So closure property of context-free languages. CFLs are closed under union. CFL are closed under concatenation. CFL are closed under clean closure, clean star. So you can say that. So L1, if L1 and L2 are context free, then L1 union L2 will be CFL. L1 dot L2 will be CFL. L1 star will be CFL. Homomorphism will be CFL. All these things we have already like we have already seen now. Okay, so what is the next thing that we need to see? Hmm. So the next topic actually that we need to start is Turing machine, because everything else we have already covered. And before we start this Turing machine, let's uh, let's see a topic called product automata. So let's see this topic, product automata. Let's see this. What is this product automata? So this product automata we did not see in the, actually when we were studying DFA, NFA, at that time we should have seen this product automata, but I forgot. So let me cover it here. Product automata. What is the meaning of product automata? So if you have, let's assume there is a regular language L1. For this regular language L1, you have a DFA. Let's assume this is your DFA D1, and you have another regular language, and for this regular language your DFA is D2. So you have DFA D1, you have DFA D2. Wait a second. So you can see, so you have language L1, you have language L2. For this language, both are regular languages. For L1 you have DFA D1, for L2 you have DFA D2. Now from these D1 D2 DFA, from these D1 D2 DFA, you can very easily construct a DFA for L1 union L2. You can easily construct DFA for L1 intersection L2. You can construct DFA for L1 minus L2. All these things you can construct DFA for. Okay, using these two DFA, you can construct DFA for this. And this construction is called product automata construction. Product automata construction. What is this construction? Let's see with example. So with example, it will be clear. So take this example. Let's assume this is your first language, which is even number of age. Okay, even number of age. So basically, this is your language, even number of age. So if B comes, then you know the DFA for even number of age. So any number of B comes, okay, you will remain here. If A comes, then you will go to here, and if another A comes, then you will come here. So this is your even number of age. You can just check it out. This is your DFA for even number of age. Let's call this is your state 1. Let's assume this is your state 2. So this is your DFA D1. What is the language? Language is even number of age. This is the language. Now let's have another DFA D2. What is another DFA D2? This is your you can say DFA D2 is number of B are odd. Number of B are odd. So this is your DFA D2. Number of B are odd means if you have a B, then you will accept it. If you have another B, then you will not accept it. And the number of A does not matter. So you can see this is your DFA D2. What is the language of D2? The language of D2 is odd number of B's. The language of D1 is even number of A's. Okay, so you have D1, D2. So basically you have two regular languages. For those regular languages, you have two DFA, D1 and D2, two DFA you have. Now let's find out how to make DFA for L1 intersection L2. Let's find out. Okay, so let's call this state P, and let's call this state Q. So you have state P, state Q, state 1, state 2. So these things you have. Now what we will do, we will try to find out DFA. We will try to find out DFA for L1 intersection L2. So how to do it? So what we will do something called product automata construction. What is product automata construction? This is very easy. Where will you start? You will start in the initial state of both DFA. Initial state of both DFA. The initial state of DFA D1 is 1. Initial state of DFA D2 is P. So basically you will start in 1P. In this state you will start 1P. Okay. This is the state in which you will start. So this is the first point. You will start in the initial state of both DFA. So this the initial state of D1 is 1, The initial state of T2 is P. So in this state you will start. Now, what we will do in this state, we will make transitions on A, we will make transitions on B. So from this state, where will you go on A? Where will you go on A? So when you make transition on A, then what you need to do? Just you need to find out where this one will go on A and where this P will go on A. This one will go on A to 2, and this P will go to P. So basically you will go to 2P. This is how to, so this is how this product automata construction works. Very easy, you can see. Where will you start? You will start in the initial state of both automata. Now, once you have this initial state, now what you will do? You will make transitions on each input symbol. So now you are making a transition on the symbol A. When you make transition on symbol A, then what you need to do? Very easy. Just find out where this 1 will go on A, where this P will go on A. So this 1 will go on A to 2, this P will go on A to P. So this is how basically from 1P on A you will go to 2P. Let's see where this 1P will go on B. Let's see where this will go on B. So this one will go to 1, you can see. This 1 will go to 1 on B. On B, this 1 will go to 1, you can check it out here. This P on 1, it will go to Q. So basically from 1P where you will go? You will go to 1Q. So from 1P on symbol B, you will go to 1Q. Okay. So now we have done all we have done all the transitions of 1P, because you have only two input symbol, and from each state on every input symbol you need to define the transition. So we have completed this 1P. Okay, this 1P is completed. Now let's complete 2P. So tell me where this 2P will go on A. Tell me where this 2P will go on A. We will try this. Where this 2P will go on A. No, see, see here, see, this is 2P, okay, and you want to check out where this will go on symbol A. So what you need to do? You need to check out where this 2 will go on A, where this P will go on A. So this 2 will go on A to 1. You can see this 2 will go to 1 on A. So this 2 will go to 1. So this 2 will go to 1. And this P will go to P. So finally, where will you go? You will go to 1P. Basically, on A, you will go to 1P. On A, you will go to 1P. Your answer will be 1P, not 1. So from 2P, you will go to 1P on A. Okay. Now tell me where this 2P will go on B. Where will this go? Where this 2P will go on B? Tell me. Try this. Where this 2P will go on symbol B. So you can see, first of all, this 2 is going to 2 on B. This P is going to Q on B. So where will you go? You will go to 2Q. So you will go to 2Q. Basically, you will go to 2Q. 2Q. You will go to 2Q. On B. On B, you will go to 2Q. Now this 2P is covered. So let's cover this 1Q. Where this 1Q will go on A? Tell me. Where this 1Q will go on A? Aditya, any doubt in this? Tell me where this state, from this state 1q, where will you go on the symbol A? So you can check it out. See, from 1q, where will you go on symbol A? So this 1 will go to this 1 will go to 2, and this q will go to q. So basically you will go to 2q. So from 1q on A, you will go to 2q. From this 1q on A, you will go to 2q. So this is how you will make. Now from 1q, where will you go on symbol B? Tell me. From 1q, from this state 1q, from this state 1q, where will you go on symbol B? So you can see this 1 will go to 1, and this q will go to P. So where will you go? You will go to 1P. Basically you will go to 1P on symbol B. Now this state is also covered. Now let's cover the state 2q. So where will this state 2q go on A? This state 2q, where it will go on symbol A? Tell me. So you can see this 2q, where it will go on A? This 2 will go to 1. Okay, this 2 will go to 1, and this q will go to q. So basically you will go to 1q. So from 2q you will go to 1q on symbol A. Okay, anyway, there is like lack of space here, but you know that from 2q you will go to 1q on symbol A, and from 2q where will you go on symbol B? So you can see from 2q on symbol B, this 2 will go to 2, and this q will go to P. So you will go to 2P. You will go to 2P on symbol P. This is how you can construct a product automata. Now, why this product automata construction is important? Because once you do this construction, now you can basically, now actually you have got the, in this same DFA. Okay, you have got a 4 state DFA. You can see 1 2 3 4 state are there in this DFA. Now in this DFA, if you make 1 and q, because here this 1 is final state, here this q is final state. So if you make both of them final, then this DFA will accept the language intersection. Like if you want to make, a DFA for the intersection of these two languages, this is your L1 language, this is your L2 language. If you want to make DFA for intersection of these two languages, L1 and L2, intersection of L1 and L2, then what you need to do, because you are making intersection, so basically the string also should belong to here, and the string should also belong to here. Means basically you will make final state 1 and q. This will be the final state. This 1q will be the final state. This will be your final state. This 1q. So you can see this 1q will be the final state. So if you make this 1q as final state, then your DFA will accept L1 intersection L2. Okay. Remember, if you make this 1q as final state, then you will get intersection language. Okay. If you make, for example, because this 1 is final state, so you make this final state, you make this final state, and this q is final state, so you make this final state. Basically, you are making every state in which you have either 1 or q. You are making all these states in which you either have 1 or you have q. You are making them final. Then what it will accept? Now it will accept L1 union L2. Now it will accept L1 union L2. So this is the product automata construction. This is a very easy construction. Let me tell you. You have a DFA D1. In this DFA D1, okay, like you have some DFA D2. You have some DFA D2. Now let's assume you want L1 intersection L2. Then what you can do? You can do the product automata construction. Very easy. This construction is very easy. I told you, where will you start? You will start in the initial state of both DFA. So you will start in the initial state of both DFA, and then you all you need to do is just make transitions on the input symbol. Make transition on A, make transition on B. Just keep on doing, keep on doing. Okay. Now, finally, you want L1 intersection L2. So what you will do? You will make, for example, let's assume in this DFA D1, let's assume in this DFA D1, the final state is A. Okay. In this DFA D2, the final state is, let's assume 1. Then in L1 intersection L2, the final state will be A1. This will be the final state. Only this will be the final state. So this is how you can find out L1 intersection L2. Now, how to find out L1 union L2? Let's see how to find out L1 union L2. The same thing you will do, the product automata construction you will do. Okay, the same product automata construction you will do. But at the end, because you want L1 union L2, let's assume in D1 the final state is A, in D2 the final state is 1. Okay, in D2 the final state is 1. Then in L1 union L2, okay, you will make the product automata construction. Okay, and the product automata construction we have seen. And in this product automata construction, what you will do, wherever you either find A or you find 1, make that final state. For example, if you find A here and 2 here, so you will make it final state. Why? Because either you find A or you find 1. So either you find A or you find 1. Then all those states where you have either A or you have 1, all those states will be final state. So this will be your L1 union L2. This will be your DFA for L1 union L2. So this is the complete idea. Okay, so this is your product automata construction. Let's take one example. You can try this example. Let's take it. So you try this question. Let me take this DFA, and your DFA is even length strings. Even length strings. So this is so you can see your DFA is even length strings. This is your DFA. Let's call it 1. Let's call it 2. This is your DFA even length strings. And another DFA that you have. Let's have another DFA. So this is your DFA D1. Okay, let's have another DFA D2, and that DFA is like sigma star A intersection B. You can see this is your another DFA. Let's call it P. Now try the product automata construction of D1 and D2. Try the product automata construction of D1 and D2. So let me start you. Okay, very easy to start. In the product automata construction, what we do? It's very easy. We will start in the initial state of both automata. Initial state of both automata means 1 comma p, because here the initial state is 1, here the initial state is p. So you will start in the initial state of both automata 1p. In this state you will start. Okay, now all you need, so this is the starting point. Now it's very easy. What you need to do, you need to make transition on A. Where you will go on A? Tell me. Where will I go on A? Tell me. So I will go on A. Where I will go? I will go to, on A I will go to 2p, because this 1 will go to 2, this p will go to p. So I will go to 2p on A. Where will I go on B? Where will I go on B? From here, from 1p, where will I go on B? Again 2p. So you can see whether this A comes or whether this B comes, I will go to 2p. Now, so this 1p is done, you can see, because from this state you have completed transitions on all the input symbols. So this state is done. Now try, let's cover this state. Let's cover this state. From 2p, where will you go on A? From 2p, where will you go on A? So you will go to 1p. From 2p, where will you go on B? From 2p, where will you go on B? You will again go to 1p, right? Because this 2 will go to 1 and this p will go to p. So from 2p on B, you will go to 1p. And you can see now this state is also covered. So you have covered everything. You can just check. This is your product automata. Now If you want L1 intersection L2, then what you need to do? Tell me. If you want L1 intersection L2, then which state you want to make final? You want to make L1 intersection L2, then which state should I make final? Right, I should make this state final. Because I want L1 intersection L2, I want intersection, so I want this final state and this final state, means 1 comma p. This will be our final state if I want L1 intersection L2. Now this is your L1, like this is your DFA for L1 intersection L2. This is the DFA for L1 intersection L2. What state should I make final? Let's assume you have this thing. What state should I make final if I want L1 union L2? Tell me. I want L1 union L2. Now, which state should I make final? Right. Because now I want L1 union L2. So, which state should I make final? See, now I want L1 union L2. This is what I want, L1 union L2. So in the L1 union L2, the final state will be either this or this. Okay, either this or this means basically like this, either this or this. So basically here you can see this will also be final state and this will also be final state if you want L1 union L2. So this is your DFA for L1 union L2. Anyway, this is how you can make the product automata, and you can use this product automata to find out the DFA for L1 union L2 or to find out the DFA for L1 intersection L2. Very easily you can do. This is your product automata construction. Okay, so this product automata construction is an important construction because if you have to be D1 D2 and you want to find out L1 intersection L2, okay, you want to find out DFA for L1 intersection L2. Very easily you can find out using the product automata. Just make the product automata, and once this product automata is done, now you can make the final state. The final state will be the final state of both the DFA. Okay, that will be your final state. Similarly, once this product automata is done, now if you want DFA for L1 union L2, then also you can find. So this product automata is an important topic because this product automata gives us, you can say, gives us DFA for L1 intersection L2, L1 union L2, all these things. For all these things, you can find DFA using this product automata construction. And this product automata construction is very easy. Okay, where should you start? You should start in the initial state of both automata. Okay, initial state, let's S1, S2. So initial state of both automata, you should start. Now what you need to do, very easy. Okay, for each input symbol you make moves. Okay, where will you go on A, where will you go on B? When you are making this move, like where will you go on A, then what you need to check, where this S1 will go on A and where this S2 will go on A. Let's assume this S1 is going to Q1 and let's assume this S2 is going to Q2. So like this. Okay, so basically where this S1 will go on A, where this S2 will go on A, and this is how you will do the product automata construction. So this is a very easy thing you can see, and this is your product automata construction. Okay, so now all these things are over, and from the tomorrow, from the next lecture onward, we will start the next topic. That is the next topic is Turing machine and decidability and all these things. So we have seen two machines so far. The first machine was finite automata. In that we have already seen DFA and NFA. The second machine was push down automata. There also we have seen PDA and DPDA. So actually four machines we have seen: DFA, NFA, PDA, DPDA. So four machine we have seen, four automata we have seen so far. Now the next automata that we will study is something called Turing machine. So this Turing machine we will start tomorrow, and the things that are pending right now are Turing machine, decidability, countability. These three things are pending. Okay, so we will see them in the next lecture, and you can try. You should attempt the previous year questions of TOC. The previous year get questions of TOC you should attempt. If you have any doubt, then you can ask me on the WhatsApp, or you can ask in the next class. Okay, so see you in the next lecture. Anyone has any doubt right now? If you have any doubt, then you can ask. Any doubt? Okay. Okay, then see you in the